Let's go ahead and take a look at lesson 5.1. I'm going to do two full examples, or one example of the doing left hand and right hand, or left end and right end point approximations. But when we start here, this can be a little overwhelming if we look at this kind of sigma notation. If it's been a while since you've had to use sigma notation, it really is a setup for the remaining part of the chapter, or the unit 5. And so it starts with just a reminder of what sigma notation is, so that we could actually get into the definition of an integral, an area underneath the curve. So I hope you don't struggle too much with this, and I won't emphasize a lot in the exam or on kind of using the sigma notation, but you need to know how to understand it and what it is, right? The sum of, right? And the reason it becomes important for us is because we end up adding an infinite number of values. And so the sigma notation is a good way for us to represent. So this is a pickup from a previous class, this sigma notation and sums, infinite sums, or sums of series, right? Notation. So it's its own kind of algebra that comes with it. So again, you want to review that and look at that. And then there are certain rules that emerge, right? Formulas that emerge from specific sums. And these are famous ones. The sum of consecutive numbers is n times n plus 1 divided by 2. So if you want to add up 1 plus 2 plus 3 all the way to 10, you just do 10 times 11 divided by 2. If you want to add squares, perfect squares, you have a formula to do that for us too. These also come out into play later on in Calc 2 and 3. We need this a little bit more. So definitely be familiar with the sigma notation that exists here. What we're going to use, though, this sigma notation is to answer a fundamental question in calculus, which is approximating the area underneath a curve. So if you never thought about that, it's our first time really looking at how do I calculate the area between the x-axis and this function? Now, this function has an irregular shape. That's what makes it difficult. If it was just a line, right, we could find the area underneath the curve using geometry tools, right? We have formulas for that, but we don't have formulas for functions like this, and that's what I want to do. So you have you get introduced to things called left endpoint and right endpoint approximations. You have all this kind of weird notation. That's what I'm going to do an example of. But again, you'll soon see why we care about the area underneath the curve. We call that an accumulation function, that somehow it's going to represent values in our world in meaningful ways. And so that's what we look at. So let's go and take a look at some examples first with this. So let me come here. And so I'm looking at checkpoint 5.4 from our notes here as you went through, or from our textbook, and you may have read already some examples here: left end, right point, left end point, right end point approximation. So in this first, in the specific example here, we're looking to approximate, and what you have here is the graph of y, f of x equals 1 over x. And just as a practice, what is the area right here? What's the area underneath the curve from here to here? This is an exact answer, right? This red part is the exact answer for this, all of this space, the area. But since this is a curved, we don't have a function or an equation or formula to use to find this area. And this became a problem, like in our world, where how do I find the area of irregularly shaped objects? And this is our beginning process. And then we learned that these areas represent a lot of other things in our world, right? There's a connection to it. So we just start with a practice problem. So how would we find the area? Well, someone said, let's just approximate it by breaking this up into approximations, into pieces that we can calculate. And so one way we do that is with rectangles. We imagine that we break this up into rectangles, something like that, right? You have these rectangles that I can find the area of a rectangle. I know the width and I know the height. The height is some value on the function. So that's what we're looking at. And so the specific task here is to approximate this using left end and right end points, n equals 4. So here's a picture of this. So there's your function again, and then there are the 4 left endpoints. So we're referring to these points right there. That's the left endpoints. That's what we're referring to. So we know we want to approximate because it's hard to find the exact, right, area. which we learn is that instead of using 4, let's use 8 rectangles or 16 or 32, right, to do it. And so you can see that you end up with 4 rectangles using left endpoints. Now to approximate that area, notice there's your height. And then here is the width. Your delta x is considered the width of the rectangles that we have here. And we just chose 4 as a way to start an approximation. We could choose 8 rectangles, 10, 100, right? 1,000,000. And so to approximate that, we have this notation here. To approximate the area, we call it L4 because we're using left endpoints. To do that, the height of this rectangle is the value of the function at x0. And we break it up, we partition it into 4 pieces. You have x0, x1, x2. That produces the 4 pieces that you look at. Now, to calculate the area, it's just the value of the function times the width. The width is constant, 0.25, because 2 divided by 4 rectangles, right? You end up into quarters, right? You end up into quarters when you divide that in there. So as we see, the distance from here to here is 1.25, right? And then to 1.5, 1.75. So you have quarters there. And so your delta x is 0.25. Your height of the rectangle will be here, f of 1. And then the height of this is f of 1.25. And then f of 1.5, f of 1.75, right? And to get that delta, again, it's 2 minus 1. That distance is 1 divided by 4, right? So that's where that 0.25 comes. And if I can calculate that, the calculator can do those easily. We end up with an approximation. This one here, because the values are over, this is what we call an overestimate of the actual value, right? An overestimate of the area. Remember, we're trying to calculate the red part, the red part from over here. It can be summarized with this notation here. L4 is the sum of f of, my dog's barking, f of x I sub 1. As you look at that there, you'll see here, again, I is 1. In this case, we're doing 0, right? From 0, 1, 2, 3. We're going those 4 rectangles because this is the height. Now, if we wanted to do a right end, it looks like this. This would be what we call an underestimate, right? An underestimate, because you see those rectangles are below, right? You have some extra space in here. And so once we have that, though, we now are going to use the right endpoints, which are in this spot here. We're still using 4 rectangles. The width is 0.25. And again, this is just a technique we use to estimate the area underneath the curve. And then we're using the right endpoints as this is an underestimate. And then you have this. This is what this is how you would do it. Find the height of those right rectangles, right? The right endpoints. And that's where you're substituting into the function 1 over x. You would get those values multiplied by 0.25, and then you get this, which is smaller than this one because, yes, it's an underestimate, this is an overestimate. Now, those would be our estimates for the area. Some people may find the average of that, add that in that one, and then that's a better estimate, which is possible. Again, here's the formula we're using, the sum of the function times the width from 1 to 4. In this case, it's x sub I because we're using x1, x2, x3. Now, this right end here turns out to be an underestimate. The left end turns out to be an overestimate. It doesn't always work that way, left and right. Sometimes the left end is a lower and then the right end is an upper. It depends on the direction of the curve, what the function is. All of this, though, allows us to define how to actually calculate the actual area, which turns out to be a limit, right? In this case, we would define the limit as n approaches infinity of the sum of f of x times 0.25. F of x is 1 over x as I equals 1 to n, as n approaches infinity. So we can actually hand calculate those limits to actually find the value as we go to an infinite number of values. So that's the power why we start the setup of just estimating, which leads back to this idea of the limits, right? And you can see, where's the picture, as we increase the number of rectangles from 4 You can increase to 6 to 7, right? You end up with that definition. Where is it again? There it is again. The definition of the area underneath the curve. So hopefully that helps a little bit looking at that example. And we're going to use that idea moving forward.